Hello. Now I'm going to show you another exercise. First, I'm going to show you a diagram in here, like this. So, this is an electromotive force, okay, or a voltage, or a difference in voltage. That means that, for example, you have a negative, you have an excess of negative charge in here, and a lack of negative charge in here. Okay, so this is kind of positive, this is negative, like this. You have a bunch of negative in here, and you got a bunch of positive here, okay? And these charges cannot be together by the negative coming this way and the positive coming this way. They're blocked. There's some kind of wall in here, okay? That separates these two charges. So negative attracts positive, and the only way that the negative can be together with the positive is the negative traveling over here and coming out the other side. So this difference in potential is called voltage. Okay, so here's a switch that can be closed or open. When it's open, there's no current, right? Because all these negatives are going to come in here, and they're coming and they're coming, and they're just going to stop over here. They don't have anywhere else to go. All right. So when it closes, there's a current. The I in here is a current, and the R is the resistance, okay? And the L is the inductance. Now, as the current comes, you see, because it's a serial thing, this is in series with this. First, you got to go through this, and then mandatorily, obligatorily, you have to go through this. You don't have any parallel tracks to go side by side. You got to go one right after another. So because it's in series, there's going to be a voltage drop, okay, across all these devices. There's going to be a voltage drop in here and a voltage drop in here. And theoretically, of course, in real life, it's not like this. E is going to be equal to R, I. I'm going to put I in lowercase here. I know that it's in uppercase here, but I'm going to leave it in lowercase. Plus L d I dt. You see? So there's going to be a voltage here. This is voltage 1, for example, and these two are voltage 2. Okay? And these two have to be equal to the voltage total, all right, which is provided by the battery here. But here's the thing. The voltage of the inductance is according to the change in current. Okay, so in the beginning there's no current. As soon as you close in here, the current begins to be starts becoming larger and larger and larger and larger. And as long as it's changing, then there's going to be a current in here. There's going to be a voltage drop in here. Okay, but at one point the voltage is the current's going to stabilize. It's not going to go over or under. It will not go up or down. Okay, it's just going to stay the same. When it stays the same, this thing here becomes a zero because there's no change in current with respect to time anymore. The change is zero. Okay, so this is going to be zero, and the total voltage is going to be equal to the first voltage here. The resistance times the current. Okay, this is physics, right? Electricity in physics. All right. So, knowing that, you can say that current, well, yeah, I'm just gonna say L d I dt, right, plus R I equals E. Well, we're just gonna isolate this di dt, okay, so I'm gonna divide everything by L. So this L has to come here, and it has to come here. All right. And now I'm going to divide here and divide here. So we know what this is, right? This thing here, the u of t going to be equal to e to the integral of r divided by L with respect to time, which is just going to be RT divided by L, okay? Right? It's going to be equal to this. And then you say that I, the current as a function of time, is going to be 1 divided by U of t. It's that same scheme. The integral of QL, right? Or of QT, which is going to be E divided by L times U of t. So times, I'm just going to say U of t here, dt. That's the thing. All right. Now, if we do that, yeah, I think there's more space down there. Okay. So if we do that, you see what you're going to have is I equals, this thing is 1 divided by this, so it's just going to be E to the well, you can integrate this stuff, okay? It's going to be it's going to be E RT divided by L, but because this is in the denominator and I'm putting it in the numerator, it's going to be E to the minus RT divided by L, right? Times the integral of what? Well, yeah, it'll be E divided by L and times that stuff, which is E to the integral of, well, it's just going to be the same thing, right? It's going to be E to the RT divided by L. So you have to integrate that dt. That will be the thing. Okay, this is just generic. Now, here's a real example. The real example says, by Li, 1 divided by N, instead of being 1, it says that this thing here, I'm going to erase this. I'm going to erase everything else. It's going to be the sine of 2t. There. Okay. So the u is going to be this one, right? The u is going to be that one. So what's going to be I? I is going to be equal to E to the minus RT divided by L times the integral of E. Now this is going to be the interesting part. R over L dt. Okay, E to the R divided by L dt. Yeah. Or actually, I've already done that. I've already took care of this. So it's going to be like E to the RT divided by L times this, times the sine of 2t. Now divided by L. L is just the inductance. It's a property, it doesn't change. So when you're integrating everything with respect to t, you can put the inductance as a constant, okay? I'm just going to put an L here, a big L, okay? All right. Now here's the thing. You have to integrate this stuff. So you have E to the RT divided by L and sine of 2t. In order to do this, you have to use a technique that I haven't explained yet, which is called integration by parts, and I'm not going to. So I'm just going to give you the full answer. The answer is going to be I equals 1 divided by 4L squared, 4L squared plus R squared, okay, times, let me see here, times R sine of 2t minus 2L cosine of 2t, okay, and it just keeps going, plus C times E to the minus RT divided by L. This is going to be I as a function of time, okay? I as a function of time. Okay, that's it. For now, that's it. Oh, you're not going to show the integration by parts? No, not now. There's a right time for everything. So why did I show this example? For completeness, for you to know something about physics, okay? Okay, now there's something else that's going to be interesting. It's time to talk about Bernoulli's equation. Okay, so we've learned how to solve something like this. Y prime, right, plus P of x, and then you have a y equals Q of x. So this is what we've learned so far, all right? You can solve this by doing the scheme that we're doing. It's going to be like, because you see, I can do this, y to the n. Now, if n is equal to 0, then this doesn't exist. And I can just, the equation is linear. This is going to be a first order linear differential equation, which is going to be solved by the way we've been solving. If n is equal to 1, then this is going to be not linear, but you can still do it by separation of variables. Now, if n is higher than 1, then you got to use Bernoulli's equation. And what is that? Well, first, I want to isolate this thing. How do we do that? You multiply the whole equation by y to the minus n. So let's do that. Y to the minus n, y complement, plus P of x, y. Now, you see, y to the minus n. But you got a 1 in here, you got a y to the 1. So 1 minus n is 1 to the minus n. Very simple. Equals Q of x, all right? Now let's just think about this thing here. What is that? You see, you're still trying to, you want to make this become a linear differential equation, a linear first order differential equation, just like you had with this. Think about this equation here. Forget about this stuff and think about this equation. I'm trying to transform this equation into this. Okay? So here's the thing. Here you have a derivative of the y. And here you have a y to the 1 minus n. So you can say that we're still using the product rule of the differentiation, right? D of uv is going to be equal to u dv plus v du. We're still using this, right? Or if you want to do it thinking about f and g as two things, you want to do f g derivative plus f derivative g, right? So in here, you can see that this is not being integrated, it's not being differentiated. It's 1 to the 1, y to the 1 minus n. And here it is being differentiated. So guess what? The original thing is going to be y to the 1 minus n. When you differentiate this stuff, what are you going to get? Differentiate this with respect to x. So what do you have to do? You got to differentiate it with respect to y, and dy with respect to x. What's going to be the result? Well, it's going to be 1 minus n times y. 1 minus n minus 1 is just minus n. So to the y to the minus n, right? Times y prime. Look at this and look at this. It's almost equal, but there's a problem. In here you have a 1 to the minus 1 minus n multiplying the whole thing, and here you don't. So put the 1 to the minus n in there. Right? Multiply everything by 1 to the minus n. So let's do that. 1 minus n y to the minus n y prime plus 1 minus n times p of x y 1 to the 1 y to the 1 minus n equals 1 minus n q of x. All right, and now there's something else that we're gonna do. We're gonna say that I'm gonna put this like this, okay? Just a little thing. We're gonna say that y to the 1 minus n equals z. Why? Because you see, this is still not, forget about this thing and think about this formula. I want a y to the 1, but I don't have it. I have a 1 to the y. I got a y to the 1 minus n. So what do I do? Okay, hey, yes, I have a y to 1 minus n, but this whole thing here is being elevated to 1. So let's just say that this is z. And now I got the z elevated to 1, which is what I have over here, okay? This is not a prime, okay? This is being elevated to 1. I know it's confusing. This is a prime, and this is elevated to 1. Okay, so I'm just going to undo all this mess that I made. All right, so let's go. We have 1. So what do we have in here? Now, you know what I can do? I can say that this whole thing here is going to be dz dx, okay? Yeah, dz dx. Because if you do dz, it's going to be 1 minus n times y to the minus n y prime. So this becomes dz dx. It's not dy, okay? It's dx. And over here, you have this stuff in here. Okay, you have 1 minus n p. I always do the q here. P of x z, right? Because 1 y to the 1 minus n is z equals 1 minus n q of x. Okay. So now you see, now I have, instead of q of x, I have 1 minus n times the q of x. So what? This is the new q of x, all right? And you see, when we had p of x accompanying the long linear variable in here, what was the integrating factor? The integrating factor was e to the integral of p of x dx, okay? Well, now the integrating factor is going to be this. Yeah, it's going to be this. Instead of being just this, because here, now you have this. Okay? So the integrating factor, they have d, yeah, I'm going to do the integrating factor here first. So let's say u, right? The new u of x is going to be e times the integral of 1 minus n px dx. Does this work? Yes, it works because 1 minus n is a constant, all right? So when you're integrating with respect to x, so differentiate this, well, you integrate, okay? When you integrate this stuff, okay, that's fine. Or you just, yeah, because you don't have to integrate. You see, this is just a second function. So you're going to have this function. Now differentiate this stuff, because the z is the first function, but the second function is going to be this one. So differentiate this stuff. Well, it's going to be this stuff again, because e to the anything being differentiated is e to the anything, right? Times the derivative of this. Now I integrated this stuff and it became whatever. So the integration of this stuff, guys, became question mark. And now I'm differentiating question mark. If I'm differentiating question mark, I'm going back to this stuff in here. Okay? I integrated this, I got to whatever. I differentiate whatever, I'm coming back to this. So times the derivative of this function, which is what? 1 minus n px. And there you go. All right? So all you got to do is to multiply everything now by this stuff, by this u of x, right? So you see, I'm going to do this very slowly, but it's going to be already the same thing. Dx and then you have times e to the integral of 1 minus n times p of x dx, okay? And now you do a plus, and then you have the same thing. I'm gonna copy and paste this stuff. Because I multiplied in there, so I have to multiply in here too. Okay, and then you have times 1 minus n pxz equals, and then I'm going to multiply it again. Man, there's not going to be enough room. Well, anyway, I am multiplying this here, okay? It's this stuff times, I'm going to put it down here, 1 minus n q, well, hold on, q of x. Okay, so you got to understand that this is multiplying into this. Now look at this stuff. First, you differentiated z with respect to x, and then this is the second function that you're just copying. And now you're differentiating, you're copying the first one because you differentiated z. Here I'm just copying the z. And I differentiated this stuff. So differentiating this stuff, you have this, okay? You just repeat that, and you multiply by this stuff, which is 1 minus n px, right? And here you have 1 minus n px. So it's like you have a z and you have a b function. So the format here is z prime b plus z b prime. Okay, the z prime is this one, and the b is this. And here you have the z, okay, this z here, which is this, and the b prime is this whole thing. There you go. Okay, so now you can just say that, you see, now you actually, what I can do is like this, z equals, but yeah, okay, I'm gonna do it like that for now. Well, actually not anymore. I'm gonna say, what is z? Z is y to the 1 minus n. So I'm gonna say y to the 1 minus n equals, well, 1 divided by this stuff, right? Because it's 1 divided by the u of x, so it's gonna be e to the minus integral of 1 minus n p of x dx, right? Times the integral of q. Now, what is the new q? This is the new q, okay? 1 minus n q of x. And then you have times u of x. And what is u of x? It's e to the integral of 1 minus n px dx. And you're integrating here, so this is another dx, because this is the little dx of this integral, and this is the big dx of this integral, right? So dx, and there you go, that's it. Just for you to compare, right, I'm going to show you something. First, the formula was y equals e or 1 divided by u of t, right? So it's going to be e to the minus integral of px dx times the integral of q of x e to the integral of px dx dx, right? But here's the thing, now that we're messing with this, and in the end, yeah, because you want to know what y is, you're going to have to take the square root. It's not the square root. It'll be the 1 minus nth root of everything, okay? So in the end, in order to find out y, you have to do something like this. A big root and the index here is going to be 1 to the minus n. That's the way that you actually find out what y is. Okay, but compare, you have this formula, and compare it with this formula. It's pretty much the same, but instead of y, you got y to the 1 minus n, and instead of e to the negative p of x straight, directly, it's e to the negative integral of 1 minus n p of x dx, the integral of q of x, but now you have 1 minus n q of x, and e times the integral of p 1 minus n px dx, right? So there's a similarity between this formula and this formula. Just check it out. Yeah, well guys, this is just a theory. I think it's good enough for this video, and I'm going to do some exercises using this formula on the next video. See you guys there.